Welcome pre-calc honor students to 12.1 and 12.2, a combined section where I'm going to show you both the geometry and algebra of representations of vectors. Their objectives are to perform basic operation on vectors and also use coordinates to form vector operations. Now we're going to start off by looking at some GeoGebra stuff so you get a visual idea for what a vector is. You can pause the video and try some of these things or try them after I see them, but you should definitely try and go to GeoGebra to get a sense of what a vector is. Here's vectors. They have direction and magnitude, and sometimes they're thought of as a directed distance. It's important to realize that they represent a change in position, not just one point, but a movement from one point to another. So let's look at it on GeoGebra. First thing you want to do on GeoGebra is let's just have it snap to points. We'll keep the grid and everything like that. But under Tools, under Options, do Point Capturing Snap to Grid. Now, notice we have lines over here, down here, vectors between 2 points. And now you can see what's meant by a vector. So we can start here at 1, 2, put point A down there, and here's point B at 5, 4. And notice you get these two vectors, 1, 2, 5, 4. Those two are points though, actually, right? The U, the vector U, is 4, 2. Now for some reason GeoGebra is putting the 4 over the 2, but it basically means 4, 2. So we can actually pick up this whole vector now and move it around. See that? No matter where I move it, it still is the vector 4, 2 over 4 and up 2, but we have different starting and stopping points. Okay? That's the basic idea of a vector. And then when I multiply a vector by something, like if I say 2u, it gives me this new vector v. Now I don't think we're going to be able to move this one around so much, but you can see that everything's been doubled, that v is twice as long as the original vector u. So that's what's called scalar multiplication. If you multiply a vector by a real number, you end up doubling both components and making it longer and doubling the magnitude, but you keep the angle the same. Now let's look at addition of two vectors. Let me just get rid of this one here. And let's see what happens when we take a couple of vectors and add them up. Let's come up with another vector now. Let's put it over here like this. Here's C to D like that. And I just want to move this around a little bit. There. Now to add up two vectors, we've got two vectors here, U and W. There's U, there's W. What happens when we add these two together? Well, let's look at what happens with U plus W. Adding the two vectors, we get something like that. How is that any way related to these two? Well, it's called the resultant, the result of putting these two vectors together. Let's slide AB over here like this. Actually, let's just go like this. Let's just slide CD. I take the tail of the second vector to the head of the first vector and connect them that way. Okay, so now B and C are in the same spot. And then the resultant is a vector that goes from this point, and I'm drawing a vector now, from A to D. And you see how this vector now, right here, matches that. See that? It's the same length. And look at that, by moving that vector, I'm actually moving A around, but still give me the same resultant. All right? Last thing is vector subtraction that I want to look at. What happens if we take this same thing now, instead say, and notice how we just added up the components on U plus V. 3 and 3 is 6, 2 and negative 4 is negative 2. Now let's do vector subtraction. Let's get rid of some of these other ones in here. Let's clear out A, W. The W we've got, yeah, we want to look at U and W and Z here. Here we go. Let's see what happens when we try and subtract these two. That is vector U minus vector W. I don't see it. It made it as a new vector B, 0, 6. Oh, that's because it's right up against here. Maybe we can see it better if we just move around one of these original vectors. Let's go like this. There you go. Now, where's that coming from? Well, let's move our grid here. And when we do U minus V, we have to take the opposite direction of this vector. So a vector in opposite direction, let's look at what the opposite of W looks like. Opposite of W. It's down here like this. Notice how it goes like that? So it's basically we take, and we can make the opposite of W up here. Going from here, backing up 4, going up 3. There's minus U, or sorry, U minus W. And then when I do the resultant from there to there, boom, boom. There you go. That's the same as that vector. Okay, just a little illustration of what you can do with vectors on GeoGebra. Back to the other screen now. Okay, the important thing to remember is a vector is a change in position from 2 points. So here's the vector addition I was just talking about. If this is vector U, and this is vector V, and a lot of times we mark vectors as boldface, or, sometimes if I find it too long to make it boldface, I'll just put a U over it to symbolize a vector, a little arrow symbol. You put the tail of V, so here's the tail of V, at the head of the first vector. And then your resultant goes from the tail of the first vector to the head of the second. So here's the resultant, U plus V. And that's the visual idea of how you add up vectors. You line them up end to end. So in this first example, make a scale drawing showing a force of 20 newtons pulling an object east, and another force of 10 newtons pulling the object in a compass direction of 150. That's measured clockwise from north. Draw the resultant vector and try and estimate it. So let's take a look here. Let me put one in between here. 10 newtons east. So here's our first vector. Oopsie. And I'm just going to make that a little bigger. Let's make it a little thicker. And let's make it red. There's our first vector, 10 newtons east. And then we've got another vector pulling the same object in a direction that's 150 degrees off of true north. So if this direction is east here, this is north up this way, and we rotate 150 degrees from north. So I'm going to make a copy of this one. Oh, it did not copy. There you go. Oh, now I got to paste it. Paste. Here we go. Now I'm going to take this vector and point it down like that. But it's going to be more. It's going to, well, it's only 10 newtons though, so it's like that. So there's my other vector at roughly, does that look about half as much? Let's see. About half as much, but angled down at 150 degrees like that. Now, the resultant force is going to go over this way somewhat. So what I do to add up the vectors, I've got to put them head to tail. So this one was 10 newtons east, or 20 newtons east, and this was 10 newtons. I got to take a copy of this vector, and let's copy it, and then paste it over here. There, you can get the same direction now. So now I can do my resultant as another vector like this. There's my resultant like that. That's the one we want to find. So I'd estimate it's like, well, it went past 20 now. Maybe it's more like 30 at an angle instead of 150. Maybe for an estimate here, we're going to say 30 at an angle of about, well, if that's 90 and that's 45, maybe another 25, so maybe 115 degrees or so. Now let's see how we did. We're actually calculated out now. Now we can use the trigonometry here. We're going 20 here, and then we're coming 10 down like this. And from original diagram, this was 150, I believe, right? So that was 150. So this is 60 degrees beyond here. So there's a 120 degree angle. And so we can use the law of cosines here. Let's just call this R. R squared equals 20 squared plus 10 squared minus 2 times 20 times 10 times the cosine of 120 degrees. And crunch that all out. And you get 26.46. So our 36 was a little off. And now for the angle, well, now that we got the 26.46 here, we want to figure out what this little angle in here is here. Let's get this theta. So we can use law of sines. The sine of theta is to the side opposite, which is 10, as the sine of 120 is to the side we just figured out, 26.46. And you'll get two angles. Clearly this is the obtuse angle, and from that we get theta equals 100. We'll get actually 19.1 degrees, and then to get it in the bearing off of north, so it's 109.1 degrees clockwise from north. Okay? This idea of bearing is something that's not required. I don't require you to know that navigational term and so forth. We're going to be using vectors a lot more in the component form, as we see here. Now, I talked a little bit about vector subtraction. U minus V, you're going to take U, here's U, vector U, and then let's say this is vector V. To do U minus V, you're actually going to set of V in this direction. This is the opposite of V. So, let me clean this up a little bit. This was vector U. These are the two we started with. Vector U minus V will go from here to here. So there's U minus V. A little trickier concept. You don't just add them end to end. You have to think of what the opposite of vector V is. And multiples of vector, we talked about that. KV will affect what? What do you affect in a vector when you multiply it by a scalar? KV will affect the magnitude, but not the direction. Of V. That is, if K is greater than 0. If K is less than 0, you're going to end up sending it in the exact opposite direction, like we saw with the subtraction. Okay, now we're going to use vectors V in here to do some sketches here. To do 2U plus V, I'm going to make a copy of this, copy of vector U here. Oopsie, undo. We wanted to make a copy. So, boom, and here, paste and paste. Paste. So we got a couple of vector V's here. Hello. All right, there's two U's, and I put them end to end. So that's the idea of scalar multiplication. You made it twice as long, but in the same direction. And now we just need three V's. Clone. 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 Here we go. Oh dear, that was not mentioned. Boom. Boom. There's three of these V's. And then I'm going to have to get rid of that one. Sorry. Because that one got messed up. Let's just clone this one. Drag it over here. There you go. And so resultant is going to go from where we started to where we finished like that. There's 2U plus V. Now for U minus 2V, again, we're going to need a copy of this puppy. Oh God. Leave it there. Let's clone that. So we just need one of those. Oopsie. One of these over here, and then minus 2 V's. So let's clone that a couple times. Clone with clone. And move them over here. There's one of them. Oh, but what's this? We've got to go in the opposite direction. That would be U plus V. We've got to take these guys and have it swing around like that instead. Taking both these vectors and have them go in the opposite direction like that. There you go. So there's your U minus 2V. Ends up in there. Okay. All right. Now, using components is going to be a lot easier than doing all this sketching and so forth. So the idea of vector AB comes from the displacement between 2 points, and we saw that right away when we did the GeoGebra stuff. So in a coordinate system now, when you have a couple of points here, and you go from point x1, y1, and that's A, to point B over here, which is x2, y2, and that's your vector AB. You can see how you can break it up into a horizontal part and a vertical part. And you're going over x2 minus x1, and then you're going up y2 minus y1. And that's how we come up with the components of vector AB. Now the magnitude of it just employs the Pythagorean theorem then, because this is a right triangle now. C squared equals A squared plus B squared, and we can use this. I think you've seen this before, but this concept is kind of new, that you have to make sure you understand when a problem's giving you a point versus when the problem's giving you a vector. So here's example 3. Given 4, 2, and 9, negative 1, express AB in component form and find the magnitude of AB. Well, let's throw in a little graph paper here. Sorry, I should have called this up earlier. It's under My Stuff, Graphing, Pictures, and it's an XY axis. Here we go. Grand. Let's make it just a little bigger here so we can get it all on there. Right, 4, 2. So here's A at 4, 2. 4, 2. There's point A, and point B is 9, 5, 6, 7, 8, 9, negative 1. There's point B. Express AB as this vector like this in component form. So for AB, we're going to do the change in x's, which is 4 from A to B, which is negative 1, minus, I'm sorry, I have to look at the x coordinates, 9 minus 4, and the change in the y is negative 1 minus 2. So we get 5 common negative 3. And that's what we've got here. We're going over 5, 1, 2, 3, 4, 5, and down 3, 1, 2, 3. So those are the components of that vector, over 5 and down 3. Now to find the magnitude, and that's what that absolute value stands for, we just do the square root of 5 squared plus negative 3 squared. Careful, make sure that whole negative 3 is being squared. Square root of 25 and 9, and we get the square root of 34, or a little less than 6. 1, 2, 3, 4, 5, 6, yeah. Not quite 6 long. Okay, now, careful. Use the context to decide if someone gives you an ordered pair like this, A comma B. It could be a point in the complex plane. It could be a point in the real plane, or it could be a vector in the real plane. So we can think of as vector OP like this, A comma B, where I'm giving the components. I could think of it as point AB, and I also think of the complex number AB. Remember, we also had context, too, that A comma B could mean the interval, the open interval, A is less than X is less than B. So again, you really have to understand the context of the problem to see what that notation is representing. Now back at this problem, a lot of students might have said, well, what if, let me just clone this page. What if someone were to say, oh, but wait a second, I'm viewing A as a vector. This is vector A. And B as a vector. This is vector B from 0, 0 up to this point 5, 4, 2. And from 0, 0 up to point 9, negative 2. Notice you still get the thing that vector AB equals, if you look at the vector addition of it, vector AB now, if I add it to vector A, let me actually write the other direction just so you can see the process of first and second here. Vector A plus vector AB equals vector B. So vector AB equals vector B minus vector A. So if you interpreted what I gave you as vectors instead of points, you'd still end up with the right answer if you subtracted the vectors in the right direction. So that's what I mean by the context. And so it can mean a point in the plane like this, A comma B, and it could be either in the complex plane, in which case it mean A plus BI, or we're going to focus on in the real XY axes, the point A comma B, or the vector from the origin out to AB, this vector OP there. And notice this stuff comes into play again too. Remember how we used to write in the last chapter R at an angle of theta? And we broke down the components. This was R cosine theta. This was R sine theta. converting polar into rectangular. And now we're talking about converting vectors in this sort of angle notation over here, r and angle theta, into component form. So that comes in this problem. A force of 10 newtons acts at an angle of 130 degrees. So let's establish 130 degrees first. There's the positive x-axis, and 130 degrees out of sync with that would be right about, that's about 120, that's about 130. So there's 10 at an angle of 130 degrees. There's our vector. Find f in component form. So all we have to do for the components is the horizontal component will just be 10 times the cosine of 130, and the vertical component will be 10 times the sine of 130 degrees. Okay? And to calculate those out, you get negative 6.43 and 7.66. And we usually just kind of write it like, get on, little doggy, get on, there, boom. Okay? All right. Now, example. Now, vector operations with coordinates is so much easier. Oh, look at this. Check this out here. Here's our vectors v and u we're trying to add up. Here's vector v and vector u. And if I have the component form, like this is a comma b, and then I'm going to go over another c and up another d, so this is a plus c comma b plus d. Because basically what I did here with vector w, I moved it out of its usual stand position starting at the origin over this way, and this means go over c and up d. So that's why we added c on. So here's v plus u. That's vector addition. Vector subtraction, I took the same vectors again. Here's vector v. This is the opposite of vector u as we head down this way. And so here's v minus u. And you end up subtracting the coordinates. Scalar multiplication, you just end up multiplying the magnitude, but notice it keeps the same direction. Even though you've changed both components, you've changed them proportionately so that you get the same slope and then the same angle with the x-axis. So in example 5 here, if u equals 1 comma negative 3 and v equals 2 comma 5, find u plus v. Well, we can just fly through this. You just add up the components. It's so much easier in component form. We can just say 1 plus 2 and the comma negative 3 plus 5. So we get the resultant vector of 3 comma negative 2. And for u minus v then, 1 negative 3 minus 2 negative 5 and 2 5. Make sure you subtract them. So 1 minus 2, negative 3 minus 5, and you get negative 1, negative 8. And then finally down here, 2u minus 3v, twice 1 comma negative 3 minus thrice 2 comma 5. So we get 2 negative 6, distributing the scalar multiple over all the components, minus 6 comma 15. And so it's 2 minus 6 comma negative 6 minus 15. And you get negative 4 comma negative 21. Okay? And for our last example, 2 parts. If a equals 0, 4 and b equals 6, 1, find the coordinates of point B, which is 2/3 of the way from A to B. Well, let's try and get an idea on this on our piece of graph paper. Here's some graph paper. Sure, give me some graph paper. There we go. And we're mainly, yeah, that should work out well. Let's make it a little bigger. So you're going to focus on this quadrant here. I want to focus on this quadrant. Yeah, there we go. And so here's our points. We got a point here at 0, 4, and we got a point at 6, 1. And there's our vector AB, right? AB, vector AB, is actually B minus A if I turn them into vectors. So it's 6, 1 minus 0, 4. So I get 6 comma negative 3. We're going over 6 and down 3. That's vector AB. We want something 2/3 of the way. This could get incredibly complicated if we were to try something involving the equations of circles and saying the distance equal to 2/3 and finding this distance. Oh no, it's so much easier, people. All we have to do is think of this as 2/3 of vector AB. Now, we're not quite out of the woods yet. 2/3, the scalar multiple of vector AB, is 2/3 of 6, -3, which is 4, -2. Let's draw that vector over 4, down -2, like that. Or in other words, starting here, 1, 2, 3, 4, and down -2, like that. That's 2/3 of the length, and by applying it to the vector in component form, we've kept the right direction as well. And I think you can read from right here that this is the point 4, 2. Because 4, -2 is not our final answer. That is 2/3 of the vector AB. Now we want to actually find the point P. The point P is going to be the point A plus 2/3 of the vector AB. So we take our point A, which is 0, 4, and we add on our 2/3 of AB, which is 4, -2, and that gives us the final answer of 4, 2. 4, 2 is the point 2/3 of the way from the point A to the point B. But notice the use of vectors in component form really helped us out with that. Let's do this again with, again, the same 2 points, but now let's find something 5/6 of the way from A to B. 5/6 of the way from A to B. So I could use a little more graph paper again. And now we know that we want to expand this a lot. Make it a lot bigger. So you really see what's going on here in this first quadrant. And we got the points 0, 4 and the point 6, 6, 1. That's A, that's B, and we're going to go 5/6 of the way. So we can say Q is 5/6 of the way from A to B. So you start at A, and to head in the direction of B, we're going to add on 5/6 of the vector AB. So the point Q will be the point A, 0, 4, plus 5/6 of the vector AB we figured out before was over 6 and down 3, 6, -3. So this is 0, 4 plus 5, it looks like, okay, -5/2, -2.5. So we get 5, 1.5 for our exact coordinates of Q. 5, 1.5, sure enough, that's the point Q. That's 5/6 of the way from A to B. Exactly. Flange out.